All right, in the previous videos about things like p-series and geometric series and stuff, um, we had to exactly match the geometric series or the harmonic series or the p-series or whatever. But it turns out that in the vast, world of formulas they could give you, very few of them are exact p-series. For example, this one right here, if you cover up the plus 1 over n squared, that's just a p-series with p equals 2. And we know that if p is bigger than 1, like this one is, it converges. So that would have been a p-series, straightforward, bam, bam, bam. But as soon as you uncover that one, and now it's 1 over n squared plus 1, it's like, oopsie daisy, it's not a p-series anymore. You can probably guess that if the p-series would have converged without that one, just stick a 1 in there. If anything, it probably converges better and faster because it makes the denominator even bigger and therefore makes the fraction smaller. But just saying it probably converges and proving that it does are two different things. So the comparison test is just a theorem that gives us an out to where we can say, you know what? This thing is so close to being a p-series with p equals 2. And if anything, it's actually smaller than that series. So since that one, that p-series converges, this one probably converges. And then the comparison test is a theorem that lets us say, you know what? Because it's smaller, it does converge. Similarly, if you look at this one, just offhand, you might say, that's kind of a wacky looking series, don't really recognize it, until you say to yourself, you know what? If I covered up the 1, I could then reduce this to being 1 over n. And that's the harmonic series, and that diverges. So I bet that if since this is really close to a harmonic series, I bet this thing probably diverges too. Because as n gets big, that 1 becomes less and less significant. So basically my hunch is that because the harmonic series diverges, this thing probably also diverges because it's so close to being 1 over n. But technically, because it's not 1 over n, because it's n over n squared plus 1, it's not the harmonic series. But again, the comparison test is going to allow us to sort of say, you know what? Because each one of these terms is bigger than the corresponding term in the harmonic series, this will also diverge. So that's what it allows us to do. All the comparison test is if you can come up with a series that's pretty close to the one you're looking at, it's going to tell you whether that series also converges or also diverges to the one you're comparing it to. Now there is a subtlety here, which is if you have a series that converges, like a known series, like 1 over n squared, and you can show that your series is less than that series, like it's always underneath it, each term is smaller than the one that converges, then obviously if that series converges and you're always underneath it, you're going to kind of get squoze under there, and you must also converge, right? It's sort of like the squeeze theorem, where as long as you know you're between two curves and those curves are getting closer and closer, then your little thing must also converge to that same point. But that does not apply if the thing you're comparing to is smaller. So for example, if I know that 1 over n squared converges like this to 0, as I go to the right, but my series is actually a little bit bigger, like each term of it is bigger than the one I'm comparing it to, that doesn't really help me, right? Because if I'm pinned in here somewhere, that's great. I know I'm also getting squeezed down to 0 and converging. But if I'm up here, it's like big deal. Am I 1,000 miles above that or just a millimeter? Who knows? It doesn't really tell us anything. So it turns out the comparison test only applies if the sequence you're comparing it to converges and your series is less than that series, then yeah, you'll converge too. Similarly, if the thing you're comparing it to diverges, like the harmonic does, and if your sequence is bigger than that sequence, or that series, then yeah, yours must also diverge. But like I said a second ago, if the harmonic series diverges, but your series is under that, each term is smaller than the harmonic series, then you don't actually know anything. It might turn out that your series converges. So the only two cases this applies to is if your series is smaller than a divergent series or larger than a divergent series. So if you're larger than a series that diverges or you're smaller than a series that converges, that's when this test applies. The test does not apply if you're larger than a convergent series or smaller than a divergent series. We're going to do a bunch of examples, so hopefully this will become pretty obvious what we're talking about. But basically the point is you got to be really careful in the series you pick, and then you want to list out some terms to sort of confirm whether you're bigger or smaller than the series you picked. So let's take a look at that one I mentioned on the first slide. We've got 1 over n squared plus 1, and our hunch is that this thing is going to converge just like the p-series 1 over n squared would. So my hunch is that this one, which this bottom one I know converges because it's a p-series with p equals 2. And its terms are 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, right? And we know that this thing converges by the p-series test. So my hunch is that maybe this one also converges. So what we need to do is list out the terms of this sequence or the series and make sure they're smaller than all the terms of the one we're comparing it to. So let's list out the terms here. We've got 1 over 2 plus 1 over, plug in 2, you get 4 plus 1 is 5. Plug in 3, you get 10. So let's look at the comparison. I want to make sure that for every term in my series, the corresponding one right below it is larger. And sure enough, that appears to be the case, right? 1/2 is less than 1, a 5th is less than a 4th, a 10th is less than a 9th. Our denominators are all 1 bigger than the corresponding denominator in the p-series. So basically, if you're looking at the sum of this thing, the p-series is going down like this, and ours is just underneath it because all our values for each individual term are lower than the corresponding terms of the p-series. So this satisfies the test, and since this one converges, ours must also converge. So that's how you do it. You got to list out the terms one at a time and then sort of show by observation. There's no like big mathy way to prove this. What you're going to do is you're really going to look at it and show like, hey, look, for these 5 terms, it's always smaller. And it kind of makes sense that because this denominator is n squared plus 1, whereas this one's just n squared, yeah, n squared plus 1 is always going to be 1 bigger than n squared. And therefore, this fraction is always going to be just a little bit smaller than this fraction. So that's kind of the logic of it as to why that would converge. We can do the same thing with geometric series. So if we look at this series, this might look kind of wacky, but we've got, remember the sort of tip-off that you're dealing with a geometric series, which are very easy to analyze, is that we've got a number, 2, raised to a power that has an n in it. So I'm going to say, you know what? This is pretty similar to if I just had 1 over 2 to the n. And 1 over 2 to the n is nice. Recall that this also, 1 over 2 to the n is basically 1/2 to the n, like those are algebraically identical. And 1/2 to the n is just, that's a geometric sequence series where it's going to go 1/2 plus 1/4 plus 1/8 plus 1/16. This is that one that adds up to 1, which is kind of cool. So the question is, if I want to compare, if I want to find a series to compare to the one I'm currently working on, why not use this one that looks pretty similar? They'll both have powers of 2 in them. So that's good. So let's just list out the terms of this one and see if they're always smaller than the terms of this one. Now, just as a reminder, I know that this series converges because it's a geometric series with an r less than 1. To get from one term to the next term to the next term, I'm always multiplying by 1/2. That's my r. So my r in this case equals 1/2. And since that's less than 1, it converges by the geometric series test, which I covered a couple of videos ago. So let's list out the terms here and just see if our series also converges. First term in this one is going to be 1 over 2 squared, which is 4. Next term is going to be 1 over 2 to the 4, which is 16. And it's going to be 1 over 2 to the 6th, which is 64. And then next one's going to probably be 4 times bigger, so that'd be 1 over 256, ... So, did this work out? You'll notice that this term matches this one, and this one matches this one. So there might be some confusion as like, well, which terms are corresponding? Well, what I really want to show is that the sum of this series here is going to be smaller than the sum of these. So it makes sense that, well, hey, if 1/4 is here and 1/16 is here, so basically every term that's in my series is also in the series I'm comparing it to. But that series also has some extra stuff that's going to make its sum even bigger. So that's one way to say, you know what, the sum of this series that I'm looking at is definitely smaller than the sum of the series I'm comparing it to. And since this one converges, this one also converges. So that's one way to look at it. The other way is to literally compare the first term to the first term, the second term to the second term, the third term to the third term, the fourth term to the fourth term, and just do 1 to 1, like compare them. So is 1/4 smaller than 1/2? Yes. Is 1/16 smaller than 1/4? Yes. Is the third term of this one, 1/64, smaller than the third term of this one? Yes. 1/64 is much smaller than 1/8. So term by term, it also works. So whichever way you logically look at it, the moral of the story is that as long as each term is smaller, that means this series is sort of beneath or smaller than the series we're comparing it to, and therefore they both converge. All right, comparison test. This one looks pretty funky. But you know what? This might be a p-series in disguise. So if I foiled this out, I'm not going to, but if I did foil this out, I would have 1 over n cubed and then some n squareds and stuff. I'm not going to bother with all that other junk though, because as you probably remember from when you're taking the limits of rational things like this, the only thing that matters is the highest power. Because as you go towards infinity, the n squared term and the n term are going to be much smaller than the n cubed term. That's kind of what L'Hopital's is all about. So for this one, we want to compare this to the power series this really, or the p series this looks a lot like, which is 1 over n cubed. So the question is, how does this one compare to n cubed? So as you can see, there's n cubed, and I've got, everything's positive here, so I've got an n squared term, and maybe it's got a 2 or a 3 in front of it, not sure. Point is, though, it's got some other stuff. So in this one, I don't actually need to list out all the terms. I know that this one converges because the p-series with p equals 3. You know, p is greater than 1, therefore this one definitely converges. So let's see if logically we can apply it. You know, is each term of this sequence or this series going to be smaller than these ones? They should be, right? Because if I plug in 1, for example, for n, on this one I'm just going to get the first term of 1, but on this one I'm going to get 1 over 1 plus some stuff. So like 2 or 3 or something. Maybe even 7 or 10, I don't know. There's a lot of terms there and they're all positive. And then if I plug in 2 cubed is 8, but in the denominator of this one I'm going to get 2 cubed plus some other stuff, meaning there's an even smaller fraction than this one. If I plug in 3, same thing applies. So because this term has an n cubed downstairs plus some other positive numbers, every term is going to be smaller than the corresponding terms of this p-series. So therefore, both series converge because every term is smaller. All right, it'd be nice to look at one that diverges, wouldn't it? Let's see. Oh, here's one. What a shock. So let's take a look. You'll notice p-series come up a lot here. And what's the, you know, if I'm looking at this and I want to compare it to something, what's the most obvious thing to compare it to? Just the square root of n, probably. And I don't know for sure that'll work until I just sort of write it down and see what happens. So this one's a little less obvious. Since it has a square root, we haven't really done this yet. Let's try comparing them. By the way, this is a p-series with p equals 1/2. Because we have n raised to a 1/2 power. P-series always have n raised to a power. In this case, since it's a square root, that power is 1/2. So there's a p-series with 1/2 and it diverges. So remember, to use a comparison test for divergence, each term of our series would have to be bigger than the corresponding term from this series. So it's kind of opposite. Before, when you're doing converging series, you want each term of your series to be smaller than the term you're comparing it to. But when you're doing divergence, you want each term to be bigger. Because if this thing goes to infinity and your sum's bigger than that, then your sum's going to go to more than infinity, right? And obviously infinity is kind of infinity, but the point is if they go to infinity and you're bigger than them, then you obviously also go to infinity, and therefore you'd also diverge. So let's list out the first few terms. So in this one we're going to have 1 over, 1 over 0, that's not good. Better start at 2, right? because starting, 1 over 0 is not a good place to start. All right, so we get 1 over, we plug in 2. We get 2 minus 1 is 1. And then for our second term, we get 1 over square root of 3 minus 1, which is square root of 2. And then we get 1 over square root of 3. And 1 over square root of 4. All right, and for this one, when we plug in 2, we get 1 over square root of 2. And we get 1 over square root of 3. And 1 over square root of 4. All right, so these two are pretty much the same, right? So this is one of those deals where we can find, even though they don't exactly correspond, because this one starts at 1 over root 2, and this one starts at 1 but you can see that these two terms are identical. These two terms are identical. So after the very first term, which is different for this one, everything is identical at that point. So whatever the sum of this series was is going to be the exact same sum as this series, except we're going to add 1 to it because we have this first term that the other series doesn't have. But hey, if this one goes to infinity, this one is going to go to infinity plus 1. And you might be sitting there saying, hey, but Chris, didn't you just make up this n equals 2 thing? Doesn't this 1 over root n thing usually start at 1? In which case you would be correct, yeah, and we'd actually have the 1 plus here also. So these really are identical series. But the point is that because they both diverge, they're basically the same series, and they both go to infinity, so we can say they both diverge by the comparison test. So in this case, we didn't have to find a series that was bigger than the series in question. We actually could find the exact same series as a p-series. And I just wanted to point out that once again, this sort of illustrated the point that if you have two series that are identical, like starting at the second or third term and going all the way to infinity, they're totally identical. It's just those first couple of terms that are different. Then they're still going to either both converge or both diverge. Just having a couple of constants in those first couple of terms being different is no big deal. They'll change the sum by a little bit, but it won't be the difference between converging and diverging. You really need an infinity to throw off converging and diverging. And a really related problem that we could take a look at real quick. This time we'll start at 1. But what if this had been a plus sign? So square root of n plus 1. Well, let's see. The first term would be 1 over root 2. And then we'd have 1 over root 3. And 1 over root 4. So it basically just made the denominators bigger faster. So if I want to compare this one, let's say I just walked up out of the blue and done from 1 equals to infinity of 1 over root n is my comparison, then this thing's first term would have been 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4. So in this case, if I want to compare my series, this one, when you make this a plus 1, it sort of changes the series starting point. It doesn't start with 1 anymore. And you want to compare that to this one, technically we haven't satisfied the comparison test because every one of our terms is not larger than the corresponding one. The first term here is 1 over root 2. First term here is 1. 1 over root 2 is not bigger than 1. And 1 over root 3 is not bigger than 1 over root 2. And 1 over root 4 is not bigger than 1 over root 3. So it doesn't look like we've satisfied the comparison test. But for the comparison test to hold, we can just sort of look, as long as we can find a bunch of terms that match all the way up to infinity, we're okay. So because 1 over root 2, if we just sort of truncate this one a little bit and start here and find those two corresponding terms are the same, and these two are the same, and these two are the same, we know that they both add up to infinity. So either way, we've got two divergent series. So if you're comparing two series and there's just an offset of 1 or 2 terms like shifted sideways, that's no big deal. Just circle those two and you can still use the comparison test. All right, in keeping with trying to figure out things that don't exactly work with the comparison test until we make a couple of tweaks, let's look at the terms here. So if we look at the terms of this problem, now we probably want to compare it to the harmonic series, because you notice we have an n to the first power downstairs. So there's a good chance that 1 over n is the comparison we want to make. So that'd be 1 plus 1/2 plus 1/3 plus 1/4, etc. So what are the terms of this one? Well, let's see. We got 1/2 plus 1/4 plus 1/6 plus 1/8. All right, so the question is, can we use a comparison test with the harmonic series? The harmonic series diverges, right? So because the harmonic series diverges, we're hoping ours diverges too. But for that to happen, every term of our series would have to be bigger than the corresponding term of the harmonic series. So the question is 1/2, if we compare the first terms, is 1/2 bigger than 1? Is 1/4 second term bigger than the second term here? Third term, etc. Well, here's where we run into a problem with comparing this to the harmonic series. 1/2 is not bigger than 1, but then we might look here and say, oh, wait a minute, 1/2 is, at least it's equal to 1/2, that's pretty good. So let's just kind of like throw out the 1, because, you can throw away a term or two on the beginning if you want to. So let's just instead compare the first term to the second term. So that's good, right? They're equal. At least we're not hurting. But then 1/4 is not bigger than 1/3, and 1/6 is not bigger than 1/4. So we're getting in trouble here. No matter where you start your sequence, it's going to start being that your terms are not bigger than the harmonic series anymore. So we've got a problem. The harmonic series diverges, but we can't show that every term of our series is bigger than corresponding terms in the harmonic series. But here's what we can do. Instead, 1/2n is actually the same thing as 1/2 times 1/n. So what we're going to do is we're just going to factor out the 1/2 and put it out front. Algebraically, this is legal, just like you can move a constant out in front of an integral or a derivative. Constants kind of don't matter, right? If you take infinity times 1/2, you still got infinity, that sort of thing. So if we take the 1/2 out front, we now have an aha moment. We're like, oh, hey, wait a minute. This is undefined because it's 1/2, and I know that the harmonic series diverges, so it's basically 1/2 times infinity is still infinity, so this diverges. Pretty cool. So that's where sometimes if you can't get the comparison test to work, often it's because there's a number somewhere that you can algebraically remove from the situation and make everything sort of work out. All right, here's another one I introduced on the early in this video that I was saying to myself, you know what, this looks an awful lot like the harmonic series, except it's got that n-1, because if you sort of look as n approaches infinity, this -1 basically doesn't amount to a hill of beans. So this is basically for really large n's, if we use L'Hopital's, the limit of these terms is 1/n, which is 0, and it looks like the harmonic. So I want to compare this to the harmonic. Because overall, if you kind of reduce powers, this reduces to 1/n. So, and just to be real clear, what I'm saying is, if we cross out the -1, because when you're near infinity, that -1 doesn't mean much, you could then cancel this n with that n squared, so that become 1/n. So that's why I picked a harmonic series. So now let's just list out the terms. Plug in 1, you get 1/0. Uh-oh, better start this at 2. So if we plug in 2, you get 1/3. If you plug in 3, you get 3/8. And you get, if you plug in 4, you get 4/15. Plug in 5, you get 5/24. And then if we look at the harmonic series, let's get 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. All right, so the question is, the harmonic series we're comparing it to diverges. So we need to show that every term of our series is bigger than the corresponding term of the harmonic series. Because we're testing for divergence, because we have a hunch this thing is going to diverge. So let's take a look. 1/3 is not bigger than 1, so let's avoid that. 1/3 is not bigger than 1/2. Let's throw that one out. But look at this. If we start with the third term of the harmonic series, we've got a 1/3 and 1/3. That's awesome. So we're doing pretty well. 1/3 is the same as 1/3. Or if you really wanted to, you could even... Anyway, so I would just start there. with identical first term, because very often the two sequences will have the same first term. And then we could do 3/8. Is 3/8 bigger than 1/4? Yeah, it is, because 1/4 is 2/8. Is 4/15 bigger than 1/5? Yeah, 1/5 would be 3/15. 3/15, but this is 4/15, so that's bigger. 5/24 is bigger than 1/6, etc. So this works if we just sort of compare this series to the truncated harmonic series. Or if you really want to go nuts, you could throw out the 1/3 as well. You'd realize 1/3 is bigger than 1/4, 3/8 is bigger than 1/5, 4/15 is bigger than 1/6. As long as you can find a one-to-one correspondence to where you're sort of accounting for, once you throw out your terms, every term needs to be matched up against the term of the other series. But you can throw out as many as you want to at the beginning. So, looks like these both diverge. All right. Comparison test, once again. Now this one, hopefully if you just look at this, you'll realize really fast, man, I bet this thing converges. Because n to the n, it's like, if n was a constant, it would converge, because it would be a geometric series. If this n was a constant, it'd be a p-series, which converges. This denominator is going to get really big really fast. Our first term is 1, but then we got 1 over 2 squared, which is 4. And then we got 3 cubed, which is 27. Then we got 4 to the 4th, which is 256. And then we got 1 over 5 to the 5th, which is, man, I don't even know, but that's like a really big number. So point is, these terms get really small really fast. But we can't just look at something and say, you know what, that looks like it converges and walk away. We have to find a series that converges that satisfies the comparison test. So we got to find something where that converges where every term is larger than terms in your series. So you basically want every term of your series to be smaller than the terms of another convergent series. And I would pick, why not do 1 over 2 to the n? Because that's a basic geometric series. So 1 over 2 to the n is going to give us 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. All right, so, we have a problem. Is 1 smaller than 1/2? No, it is not. But 1/4 is smaller than 1/2. So let's just truncate our series. We just throw away a constant at the beginning if we want. 1/4 is smaller than 1/2. 1/27 is smaller than 1/4. 1/256 is obviously smaller than 1/8. You can see that once we get past like the second or third term, it's super obvious that we're way underneath this geometric series. So they both converge. But it turns out we could have compared this to a lot of different series. What if we compared this to a p-series, 1 over n squared, that also converges? Well, the terms of that series are 1 plus 1 4th plus 1/9. Oh yeah, this is the one that's powers perfect squares. So let's try comparing our original sequence, this guy up here, to this p-series instead. Well, let's see. Once again, in this case we have a 1 and a 1, so we'll just throw away the 1s. And then we got 1/4 is equal to 1/4, so far so good. We could just throw those away if we wanted, or just say that doesn't matter much. But then as soon as we get to the third term, 1/27 is a lot less than 1/9. 1/256 is a lot less than 1/16. You can kind of see that these terms, as soon as we get past those first couple of terms, the our sequence is way underneath this other convergent sequence. So with one like this, where the terms get small really fast, it turns out there's a lot of good ideas for stuff we can compare it to, and the comparison test will work. So that's one nice thing about the comparison test, is that if a sequence is, or if a series is right on the edge of where it's just barely convergent or barely divergent, it might be a little tricky to find something to compare it to. But there is no one right answer to what you have to compare it to. Anything you can come up with that compares favorably, like is either smaller than the, where your terms will be smaller than a convergent series or bigger than a divergent series, you can use whatever you want, and there is no one right answer. All right, last one we'll look at is this puppy. It says use comparison test, But I'm going to tell you right now, that's going to kind of be a dog. I'll show you what I mean. So n factorial. I mean, I don't even know for sure that this thing is convergent, to be honest with you. Let's take a crack. I'd be tempted to compare it, because I have an e to the n, I'd be tempted to compare it to the geometric series of 1 over e to the n. The problem is this n factorial is going to mess that up. So n factorial obviously makes the numerator bigger, so it's going to be hard to find the matching terms. Then even if it worked out, it's going to be a lot of math. And then conversely, if I tried to find something with n factorial in it, well gosh, I don't even know one of those. So it turns out this is just really badly suited for the comparison test. If you have to use a comparison test, by all means, list out all the terms of 1 over e to the n, and you're going to need a calculator because they're going to have a lot of e's in them, right? So it's going to be really tricky to figure out, well, hey, is 16 over e to the 4th bigger or smaller than 1 over e to the 5th? I don't know without plugging it into a calculator. Or is it e to the 6th is the one that matches, you know? It's going to be really difficult. It turns out we're going to want to use a different test called the ratio test. Anytime you have a factorial and stuff, it's really hard to use any of the tests except for the ratio test. But as you'll see in the ratio test video coming up, if you have a factorial, the ratio test makes factorials just totally go away really easily. And the ratio test is also really great for any time n is in the exponent, because that's also going to make a lot of stuff cancel out. So it turns out that the reason they teach you the ratio test sort of late in the chapter is because it sort of makes a lot of what you've done before irrelevant. And that's why we're going to have a good time in that video. I'm not sure if it's the next one or the one after that, but keep in mind, anytime you see a factorial, especially, and also if you see n as an exponent, the ratio test is going to be better than the comparison test, which can get really cumbersome for these more complicated formulas.